like people are like in different time zones, so they all of them might not be able to join this call. So what we are gonna do is like we're gonna record it and we would upload it so they would be able to see it later on whenever they are free. But I mean, still we will like wait for another 5 minutes and we'll see like means if some of them get time to join this call. But meanwhile, we'll try to get introduced to each other. Uh, so I'll start with myself and then. We will have like a small chit chat. Maybe you guys also let me know who are you and where are you from and what are you doing. It would be like good icebreaker if you want to participate. So basically, yeah, let me start. So my name is Mayur, and I recently finished my master's in robotic systems engineering from RWTH Aachen University in Germany. And before starting my master's, I'd been like working with firms like Tata Motors and then with Dole Controls. And after moving to Germany, I worked with FEV and Siemens. And right now, I'm working with a firm called Deonti, and we are generating scenarios, or we are building a platform where people could generate scenarios to validate autonomous driving features just with text input. So that's something we are doing at Deontic. And apart from that, I also started like my own hurdle, and it's called Cloud Robotics. So this course would be like delivered under the banner of Cloud Robotics. And at Cloud Robotics, what we are doing is like we are trying to build a platform for physical AI. So if I could give you like brief intro, then it would be like means AI integrated with like real world systems or robots. And in case of the physical AI, what we are offering like end-to-end pipeline where people could start with text input or prompt, and it would be converted into physics accurate 3D scenario, and we could like generate synthetic data for like thousands of scenarios, and that's something could be used to train foundational models. So we are building this platform. We've been recognized by our university and Deloitte. Recently, we've been selected for this program solution, sorry, problem solution fit program that's run by Deloitte and RW Chakan University, and we are also being considered for like exit scholarship. So this is like a grant from German government. So these are the things that are happening at my end. But the reason I wanted to conduct this program because, as I mentioned, I had been working in this domain for like 4 and 5 years, 4 or 5 years. But before coming to Germany, I was working with Dorley Controls, and over there I used to deliver these sessions and had like more than 100 students uh, who uh, who joined me, and we had like this in-person sessions. So it's like same program that I delivered back in 2020 until 2022. So this time I'm doing it like separately and on my own, and I'm sure because I'll try my best to give out like the best content and all the things that are there. But I mean, if there are something that I'm missing, then going forward I would be creating like more courses, uh, and that something would be made available to you through my platform or like uh, company web page. So that's about me and what exactly I'm working on. And
Sorry,
if I could,
Mayur.
sorry,
There are few guys in the group are writing. There are three people are waiting to join the meeting. So can you just admit them?
yeah, yeah, actually there are a lot. Yeah, 16 people are there. I mentioned. Perfect. Thanks a lot for letting me know because I would have like forgotten that. Anyway,
I just saw the notification in my phone on the side, so I just saw it's in the group. So
You
I just
yeah,
wanted to let you know.
use this capability for someone else so that they can keep on monitoring if somebody is joining while you are presenting, so that you are not.
yeah,
Just,
yeah. Ashwin, are you there? Yeah, yeah. I'll ask Ashwin. Ashwin, are you there? Ashwin, can you hear me? You're on mute. Okay, maybe Dipali or someone else, whoever is like available, just let me know if there is someone in waiting room. I don't know whether you guys could see it or not, but anyway, I would be like keep checking it frequently. So
Dipali here. Hi.
sorry.
You said something?
Yeah. I was saying like means if you could like see the people who are trying to join this call, and if they are in a waiting room, could you just let me know that like they are waiting over there so that I could let them in?
Okay, sure.
Okay, thank you.
You can make her co-host. Is that not a possibility?
Yeah. I would try. I would
So
try.
that way, she does not have to disturb you. I mean, she just would do it seamlessly in herself.
Yeah. I would. Why am I making it? Yeah. So Dipali, you are co-host now. So if you see some people in waiting room, just let them in, and that way it will be much better.
Sure. Thank you.
Okay. Yeah. So, guys, I was like telling about like what exactly I've been doing and who am I and why am I conducting this program. So I would not waste much time, and then we would just get started with the actual content of this program, because we have to finish it in like 90 minutes, and we have like a lot of things that we want to cover. But before getting started with this lecture, I would want to give you like brief overview of all the things that we would be covering during this program. So I've been like sending out like emails frequently for like last 1 month, and during those emails I did clarify like what all thing that I would be covering. And the first thing that I will be doing is like during this program I would be delivering like can you see my screen where I'm sharing like lecture plan?
Yes, Mayur.
Sorry, I just don't know what all things that are happening. So basically this is the lecture plan that thank you, Asha. So these are like 18 lectures that I have planned, and those lectures are something I have like split into like 5 modules. First module is about foundations, where I would introduce you guys to the basics of autonomous mobility, model-based system engineering. Then after 2 days or 3 days, I would also be delivering one more session on machine learning, and I would try to cover entire foundation right from mathematics to various traditional machine learning algorithms that are there. And if possible, I would also try to add tutorials to that. So basically, during this module one, I would be delivering foundations so that you would be comfortable to build this project later on. And whatever content that I'm delivering during these lectures would be useful for next program as well. This program is something is focused on ADAS feature development. And during this session, we would be doing like hands-on session where we would be building ADAS feature. ACC would be like built during live sessions, and then I will be giving you guys one capstone project, and that would be like LKA. So this is for this program, and then there would be like another program, and that's about like autonomous vehicles. And over there, I would be like building like full project right from simulation or like traffic simulation, and then simulator all the way perception, planning, prediction, and control. So everything would be in like ROS environment, and that's something I would be delivering later on. But during that, I mean, for that program also, the content that I would be delivering during this session would be useful. So the 18 lectures that I have planned are like first is about module one. And in module one, I would be covering like basics of autonomous mobility, basics of model-based system engineering, basics of machine learning, tools like MATLAB Simulating State Flow. And I would also be delivering one lecture on control systems. And I would try to deliver all the basics related to linear control systems. So that's something I would be delivering in module one. Then there would be like module two, and module two is something where we would be going deeper into deep learning and perception, tracking, prediction, and various algorithms that are related to perception. So that's something we would be doing in module two. Then module three is about localization fusion, and we would be like having look at both the traditional approaches as well as like state of the art deep learning based approaches for localization and sensor fusion. Then there will be like model 4 where we would be again seeing traditional approaches for planning and decision making. And finally we would be seeing module 5 that would be about controls and vehicle dynamics. So these are like 5 modules that I have planned, and I would be delivering like all these lectures, and each lecture would be like for like 2 hours long. And sometime whenever I get time, I would also try to add tutorials whenever necessary. So that's about lectures. This is the first bit that we will be doing during this program. The second thing that we would be doing is like hands-on project. As I mentioned, we would be doing hands-on project about ACC and AEB, and I would walk you through the entire procedure, right from requirement generation stage until you verify and validate your ADAS feature. So we would be building ACC AEB during this program in like 6 hands-on sessions, and then I would be giving you like one capstone project that would be about LK that you guys would be doing on your own, but I would definitely be providing like all the support, and then we would have like final presentation in the end. So that would be like second bit that we are planning to do for this session. And then third thing, as I mentioned, is like about capstone project. But capstone project is not just the only thing that we would be using to assess your performance. But apart from that, there would be like quizzes that you guys need to attend after you attend like every lecture that I am like posting on our platform or like we are conducting. So after that, you need to attend that quiz, and based on your performance during that thing, like quizzes and your capstone project, I would be giving like certificate in the end. So that's gonna be like plan for this program. Yeah. Do you have any questions regarding this plan, guys? Okay. So I assume like there are no questions regarding like entire logistics, like what all things that would be covering that we would be covering during this program. Now let's come back to like our first lecture. And during this lecture, what I would be doing is like I would be introducing you to vehicle safety, which would include both active safety, passive safety, and then I would try to take this thing gradually forward to ADAS, and then eventually we would try to see how can we extend this trajectory forward for autonomous driving or autonomous mobility. So that's something we would be doing during this lecture one. And again, for this lecture one itself, I have split it into 7 modules. And like it's easy for me also when I split particular lecture into like various modules. But for you guys also, it would be like helpful if you could look at like this particular lecture in separate modules, and then you would understand like how exactly you could like consume that particular content. So during this lecture, we would be going through like 7 modules. Module 1 would be about like introduction to vehicle safety, or like in general, we would try to build up motivation to study ADAS or autonomous driving and why exactly it's necessary. Second module would be about vehicle safety, where we would try to understand the difference between active safety, passive safety, and eventually like ADAS and other features. Then module 3 is where we would try to understand subsystem that would be necessary to build autonomous vehicles. First of all, we would try to understand about sensors. Then we would learn other elements in the pipeline, like perception and sensor fusion elements. Then we would be going over module 4. It would be about prediction, planning, and control. And so basically in module 3 and module 4, what we are doing is we are trying to, or I would try to teach the entire pipeline that we would need to implement the autonomous driving feature. So you might have heard about this particular like cycle: sense, think, plan, and act. So all those things that we would be means we just like heard: sense, think, plan, and act. So we would be delivering, or we would be like seeing in module 3 and module 4. And then module 5 is where we would see how exactly we could build these features using model-based system engineering. And once we build them with the help of like V diagram, how can we verify and validate them? What all tests that we would need to do? And once we would also be looking at like simulation, various simulation environments. And then eventually we would be having look at like various standards and regulation, because right now there are like a lot of firms that are out there. They are trying to build these autonomous driving capabilities, but the major hurdles that most of them are facing is about how exactly they could validate their feature and get that thing regulated from the government bodies. So this is like major challenge. But to ease that process, or to facilitate that, there are like various authoritative bodies are available, or like institutes are available, and they have built standards for ADAS and autonomous mobility. And that's something we would be having a look at in module 6. And then there will be like module 7, where I would just try to give you like some peek into the research trends that are like that are being followed these days for various subsystems of like autonomous mobility. let it be like perception, let it be about sensor fusion, planning, or controls. So that's something we would be doing in module 7, and then in the end we would be having Q&A session, and then we would conclude this session. So let's have a look at module 1, and let's try to build motivation, and let's try to see why do we need to study, or why do we need to work on ADAS or autonomous mobility. So there is like one statistics that's available, and according to that, from like 2003 onward until 2010, like there were like 2.25 million accidents that happened in like Germany, and means it's not like major accidents, but like overall accident that occurred during that period were like 2.25 million, and there were like 460,000 injuries that occurred during those accidents, and that led to like 6,600 deaths. So that's like really not good. Well, I mean, a number. So first thing is like all the accidents that are happening, they're fatal. Means not fatal, but like this thing itself is like not great. So we need to do something regarding that. That's like first thing. Means accidents are happening very frequently, and at the core of like all those accidents, mostly it's a driver. All the wrong decisions made by the driver, and that's something people should, or autonomous driving or ADAS mobility companies are trying to change these days. They're trying to provide co-pilot where driver would be there and he would be like observing how exactly car is being driven, but then this co-pilot is taking care of safety. So that's like one stat that we have. That's like means it's really fatal. Accidents are happening, and majorly it's because of like human driver. The second thing is about fatalities, and the number that has been dropped from the level that was there at 2001, and it's like 43%. And this decline that has happened is majorly can be attributed to the active and passive safety features. So if means I really don't have graph at the moment with me, but basically the numbers that I'm putting out over here are based on the statistics or like report that I came across. And according to that report, the fatalities that were there, they declined steeply from 1970 onward, and all that thing could be contributed to the passive safety features. It could be airbags, or it could be like seat belts and other features that are there on a car. That was like a steep decline. And then as this means all the economies are like booming, and with that there is like increase in number of cars on the road. But since there is like means increase in like number of cars on the road, there should have been like more accidents. But even with that, there is like decline in like number of fatalities 1990 onwards as well, and that something can be attributed to active safety features. But still that number is quite high. Means right now there are like 25,000 road deaths that are happening in EU annually. And during this research, the analysis that has led to like this particular conclusion is like means during this accident, the people who are really at high risk are like young people and elderly drivers. So that's something could tell us about like this whole story, that like means we need to do something to find the root cause of all those accidents, and mostly it could be attributed to the human drivers. And that's the reason we need to build co-pilot or some sort of assistance. That's something we could use to reduce this accident, or we could use to improve the safety while driving. And if you want to have like look at the database where like these accidents are noted, because these databases would be like useful when you want to like test your ADAS feature later on. So the three major databases that you could have look at are like GIDAS, that's like available in Germany. Then there is this CARE database that's for like entire EU. And then for USA, that's like this FARS database. And NHTC is like basically recording all that accidents that are happening, and there is like clear report about how exactly those accidents are happening, what all means what was the chronology. So everything is like documented in those databases, and we could use these databases to generate scenarios, and later on we could use them to build the test cases whenever we want to test our ADAS features. So that's like one thing. But the analysis that is that's there based on these databases, and like earlier report that I would share link with you for. Both of these things are saying like means mostly the accident that are happening is because of like human drivers, and we need to do something to increase the safety. And then there are like certain goals that we have. The first goal that you is like keeping before them is like by 2029 they would want to have like AB on all of their cars. uh, Same thing is also for USA, and yes, that's like also mandate for India as well. So like governments are saying like, so whenever you are like getting any vehicle, you would need to have like these basic ADAS features on that particular vehicle. And their aim is that they would want to have like accident free traffic. That's something they're calling as like vision zero, means there should not be like any fatalities during road accidents. So that's something they are trying to achieve. That's like first motivation, that these governing bodies or like people working on this problem of like this autonomous driving or ADAS are like keeping before them. Second thing, like during this accident there is like huge loss that's happening. Like these are like huge collateral losses, and that's something is like costing us around like 160 billion euros annually. So that's like huge number, and we could like reduce that if we could build really capable ADAS and autonomous driving features. The third thing means there are like various other factors that might also be useful, like political, societal impact, and also ecological impact. And all these things are like pushing us to build better and like safer ADAS and autonomous driving features. So if I could give like just one simple example, and then it's about like this ECS system. So the stability control feature has prevented all this, means most of the spin out that are happening whenever car is going around the corner. And according to them, like means they have this particular feature has like reduced vehicle crashes for like more than 30 percentage. And since they were like mandated in 2011, and that's like huge number. So if this particular one feature is like causing that huge decline in number of crashes, then there is like huge potential if you could build like ADAS and autonomous driving feature for like better safety, for better efficiency, and for better traffic regulation or like flow. So that's like motivation. That's something pushing us to build better ADAS and autonomous driving features. Now, since we have like motivation with us, like, okay, why do we need to build these ADAS features? Because it's causing accidents. Means accidents are there on the roads, and in order to avoid those accidents, we need to provide some sort of co-pilot or some sort of like intelligence to the vehicle that would assist the driver, and eventually it would like uh, help drivers to drive safely, efficiently, and comfortably. So when we try to embed this sort of intelligence into the vehicle, we need to make like small segregation between what kind of feature that we could add to enhance the safety of the vehicle. And there, according to historical trends, it could be like classified into like three stages. First is the passive safety features, and which would include like seat belts, airbags, and what basically these features does, like this feature would try to mitigate the injury that would happen during or like post crash. So that's like stage one feature where there is no active intervention made by vehicle or system, and it would just like mitigate the impact of like particular collision. Let's say it's like seat belt or airbag, and that would like reduce the fatalities or like deaths. So that's like stage one, or like passive safety features that are there. Second kind of vehicle safety features are active safety features, which would include like this ABS, ESC, that's like electronic stability control, traction control systems. And these are the features that are like uh, getting activated pre-crash, means whenever there is a particular collision that's imminent. So in that situation, these particular features would get activated, and they would try to stabilize the vehicle. Let it be ABS, let it be electronic stability control or traction control system. They would get activated in those moments, and they would try to stabilize the vehicle, and hopefully would avoid the accident that might happen later on. And the third thing, and it's about like providing like more assistance to the driver, because during this passive safety and active safety, it's more about providing the safety or more about providing the like some sort of like coverage to the driver so that there would be like reduced number of deaths. But the stage three, where people are trying to build ADAS or autonomous driving driving capability. So it's more about, it's not just about like safety, but it's also about comfort, it's also about efficiency, and it's also about delivering the like big, like a better traffic flow in congested environments. So that's like stage 3, and this is what we would want to work on during this course. That's like ADAS, this autonomous driving feature. We would want to learn how exactly we could build these features. So as I mentioned, this is just to like give you like better idea regarding passive safety and active safety features. So as I mentioned, passive safety features are the one which are like getting activated uh, whenever there is a collision. So during the collision or after the collision, these features would get activated and they would try to reduce the damage that might happen to the occupants that are present in the car. And it would include like these airbags or seat belts. And then for active safety features are the one which are actively monitoring the vehicle situation, and whenever there is a collision that's imminent, they would get activated, like ABS, ESC, ACC. Means ABS and ESC, these are like our traction control systems. So these are like major ones, and they would try to avoid the damage that might happen to the occupants or the vehicle in general. So these are the active safety features. It's just about like when, means the major thing that you need to remember is like when exactly these features are getting activated and what's their intention. What's the intention behind putting them on like vehicle. The next thing is whenever we are trying to understand this vehicle safety, when we do this classification as like passive safety feature, active safety feature, or like these automated features, we also need to understand what all factors or what all players that are there that are contributing during driving. Means whenever we are trying to define the traffic, we could like split it into like major factors. First is a driver, which is basically controller. It would perceive the environment, it would make a decision what trajectory, what like decision that need to take, and then eventually based on that decision it would like take action. So driver is like major factor inside that particular traffic triangle. Second thing is a vehicle. Vehicle is the one which is getting, or vehicle is the one which is interacting with the environment, and based on that interaction, environment is getting like change, or means environment is like getting affected. So these are like three major factors that are there, and based on the interaction between these three, this safety could be like classified or like could be categorized into four major categories, and all of these four categories of like safety uh, could eventually be converted into some sort of like safety features, let it be passive feature or active safety feature, or could be some sort of like ADAS feature. But it's just about interaction between these three major players: driver, vehicle, and environment. So whenever there is interaction between driver and environment, then that's something would be called as like perception safety. So if there are like some issues during that process or in that interaction, then that something would be converted into some sort of active safety feature uh, or ADAS feature. So that's the perception safety. And the one example that we could consider is a night vision. Let's say there is a car that's driving on like a road during night time. So at that time, visibility would be like diminished. So in that situation, there is a potential to build some sort of like active safety features or ADAS features. And that's about perception safety. Second is about like interaction between driver and vehicle. How exactly driver is interacting with that vehicle. Based on that, we could also build some sort of active safety or ADAS features. Like for example, we could build this sort of like haptic feedback, so that driver would be warned when particular ADAS feature is getting like activated, or like some other features are being turned on. Let it be like turn signal, but driver is being informed by the vehicle that it's been turned on based on that particular signal on dashboard. So that is operation safety. But if it's not, what means the signal or the light that we are seeing on the dashboard, this is something coming out of like this operational safety studies. So this is based on second interaction between driver and vehicle. Then there is a third interaction that's between vehicle and environment. So means it could have like a multitude of like interactions, or like it, there are like various possibilities that might exist for the interaction between vehicle and environment. And that's the reason we would be later on studying like this operational design domain. Operational design domain is basically like gamut of like all the scenarios, or like set of all the scenarios where vehicle would be driven, and that something is like indicative of like interaction between vehicle and environment. And in order to ensure safety during that interaction, we could build some sort of active safety features. And examples are like electronic stability controller, or we could also build ACC, or we could build like AB. So these are the features that we could build, and that's something could be categorized under this label called driving safety. And the last one is about condition safety, and condition safety is about driver's workload. So you might have heard about this driver monitoring system, because there are like various interactions that are happening between these three players, that is the driver, vehicle, and environment. And based on their interaction and based on the possibilities of like failure, we could build some sort of active safety feature or ADAS feature, and that something would help us to improve the safety of our vehicle in general. But there is one more interaction that we need to think about, and that's the interaction of driver with itself. Okay, so we need to understand the workload, we need to assess it, and based on that workload, uh, we might come up with like some features. And then this driver monitoring system could be like one of that example, where we are observing driver continuously, and we would be observing, okay, how many times he's blinking, what's the size of his pupil, and like is he yawning, and like we would be like observing his activity. And based on that, we could like come up with like some measures that something would avoid the accident, or that something would help us identify the driver when he's being unattentive. So basically, there are like four major dimension that we need to consider, or four major interaction mode that we need to consider. And based on that, we could build some sort of active safety features or ADAS features. So this is about like major dimensions. The next thing is like when we would say, means when we say like we would want to build ADAS features, then based on the way means they are like formulated, we could like classify them. So based on the support that's been provided by these features, active safety features, or like this co-pilot, we could classify them as like features which are there just to inform the driver, like this traffic sign info, or there are feature which would warn the driver whenever there is a collision that's imminent, that's forward collision warning feature. Or like the kind of feature where vehicle itself would like intervene, they would try to first warn the driver, then they do partial braking, and eventually they would do full braking. So based on the support that's provided by the system to the driver, we could classify the ADAS feature in these three categories. That's the information to give the warning to the driver and to intervene to ensure the safety. The second way to classify these ADAS features are based on this hierarchy, uh, about like how exactly and when exactly decisions are made. So we could like classify this feature into these three major categories based on the driving task. Uh, Basically, when we are like talking about this autonomous driving or automated driving, you might come across like these two terms very frequently. That's a dynamic driving task, and second is OEDR, that's object and event detection and response systems, or like also ODD. So these are like two three things, I mean, this dynamic driving task and OEDR, and these two things are like helping us to classify the ADAS features. So the first thing is like navigation. Basically, it would have like really huge time span. It could range from like 10 seconds for hours, and based on like driving task or like kind of decision making that's involved, we could like build some sort of like ADAS features or active safety features. So GPS and map based routing. So means whatever features that are provided to ensure the safety, to ensure the comfort uh, at this level, could be converted, means could be considered for like navigation stage. Second thing is for like time window from 1 second to 10 second. uh, there is like second category, that's the guidance. So whatever decisions that are made in that time frame, like lane change decision or overtaking decision, based on that we could come up with like some sort of like active safety or like ADAS features. So that's like that would be considered under this guidance category. And then there would be like features that would be there to stabilize the vehicle, like actuations and corrections like ABS or ESC. So what we have seen as of now, we have seen like motivation. Then based on that, we learn, okay, we would need to build ADAS and autonomous driving feature. Then we learn about vehicle safety, which is classified into like these three major trends: active safety, passive safety, and automated driving. And for automated driving, we learn that okay, we need like three major players, or we have like three major players, that's the vehicle, driver, and environment. And based on their interaction, we would have a potential to build various active safety or ADAS features. And then this is the last thing, like when we want to like build various ADAS feature or active safety features, how can we classify them? And that classification could be made based on the support that's been provided during that feature. I mean, whenever that particular feature is like being activated, or based on dynamic driving tasks that's involved in that process. So this is we are until this point. The next thing is there is one more way to classify these various ADAS features, or also we could extend this thing for automated driving or autonomous driving. And according to this ACE J3016 documentation, they have made like these 5 levels of autonomous driving. So level 0 is like basically no automation. Driver would be like fully responsible for driving task. Then there would be like level 1, and at level 1 that would be considered like driving assistance systems. And in at L1 level, the major factor that's something helping us to identify whether that particular feature is at L1 level or L2 level, and that major factor is like kind of control that we have for our vehicle, or kind of control that's provided by system as an assistance to the driver. So at L1 level, system would have a capability to either control longitudinal dynamics of the system or to control the lateral dynamics of the system. So either ACC or LK would be considered like driver assistance feature at L1 level. Then L2 level is the one where system would be able to control both longitudinal dynamics and lateral dynamics. And basically system would be able to perform all these dynamic driving tasks. And then at level 3, system would be able to perform one more thing, and that's like means apart from this longitudinal dynamics and lateral dynamics control, system would be able to do one more thing, and that's something called as like OEDR, which is nothing but object and event detection and response system. And what it means is like system would be able to like identify all the object in its vicinity. It would be able to identify all the events, like means some critical maneuvers like cut-in maneuver, or maybe at the intersection it would be able to identify rogue vehicle that's like crossing at the intersection. So it would be able to, the system itself would be able to identify object, it would be able to identify the event, and based on the detections, it would be able to come up with the response. So that's like level 3, and that's something would be called as like partial automation. But at level 3, system would definitely have a capability to perform dynamic driving tasks. But system cannot be like fully trusted, and that's the reason at L3 level we need to ensure that driver is means their whole time and supervising the decisions that are made by the car. And that's the reason whenever we are like at means L3 level, to ensure the like attentiveness of the driver, we tend to put this driver monitoring system over there. And like most of the OEMs that are there, most of them are like in this range, either they are like L2 plus or L3, because this is the level where we could say okay, driver is responsible for the driving task, either like through direct intervention or through supervision. But until L3 level, driver is responsible for the driving task. And most of the OEMs at this moment are like working on this L3 capability for like automated or autonomous driving. Then comes L4 capability, and for this L4 capability, the third factor that we are considering is capability, or like basically we are considering this capability uh, called like ODD, that's operational design domain. And that means whenever we are saying okay, we have built autonomous driving capability, so at L4 level we need to attach, or we need to attach basically this tag called ODD, means in what region our vehicle would work without any intervention from the driver. So this is L4 level. And Waymo is like one of the basic example of this kind of like L4 level capability, where means when they started their trials, they were just in like means this Arizona state, means they were conducting their trials in that Arizona state, or like in one particular city. So basically they had like this geofence, means a region geofence, and in that region only they were providing this capability. So whatever eventualities that might happen in that region, they would be able to come up with the response. And that was like L4 capability. And then comes L5. So at L5, we say system would have capability, or system would have like unlimited ODD, and system would be able to drive autonomously anywhere in the world. So this is like basic distinction or like classification that's been made according to SAE J3016 documentation between level 0 to level 5, and four major factors that we would be using to do this classification is basically longitudinal control capability, lateral control capability, driver supervision. Whenever system is not able to make a decision, there should be this fallback mechanism at level 3, and fourth thing would be ODD. So these are the four major factors that would be there, and based on that we could do this classification. The next thing is like what kind of like L2 features that are there. Means basically I'm just like trying to show some ADAS features to you. Just as an example, so in case of the adaptive cruise control, like ego vehicle would try to maintain certain distance from vehicle next to it. That's adaptive cruise control, and it would be happening like adaptively. Means either it would be about like headway, or it would be about like velocity. So that's adaptive cruise control. Then this is a forward collision warning, where like ego vehicle would try to warn the driver whenever it comes like really close to vehicle next to it. The next thing is automatic emergency braking system, where whenever like driver is not able to come up with like some sort of response in the event of like this imminent collision, system will try to provide like partial braking and full braking capability. That's automatic emergency braking system, which is again also ADAS feature. Then there is like lane keep assist feature, where system would try to help driver to maintain the lane or like stay at the center of the lane. And then last one is like lane change assist, where system could also assist driver to perform this lane change maneuver in a such a way that there would be like minimal jerk that would be like experienced by the driver. So these are like ADAS L2 feature, means ADAS features until L2 level that we observe. And now we would try to understand, whenever we are like trying to build this ADAS features or autonomous driving capability, let it be from like L0 to L5, what all modules or what all subsystem that would be there. So whenever we are trying to build these features, we would need to think about this one formula, which is called as like sense, think, plan, and act. So first of all, we need to sense what's around us. Then second, once we sense it with the help of like certain sensors, we need to make representation of the world around us. Based on that representation, we need to identify, or we need to predict how exactly all other vehicles would like move in future. And based on that, we need to come up with like plan for our own ego vehicle trajectory, and then eventually we need to actuate our controls in a such a way that we would be able to follow that trajectory. So basically this is like 4-stage cycle that we would be following. And to implement this 4-stage cycle, sense, think, plan, and act cycle, we would be having certain subsystems. And first subsystem is like sensors. So in this particular module, or like in this module 3, we would be looking at like various sensors that we would be using for autonomous driving. But I would want to like take a break over here, and I would want to understand if there are like some questions from your end, then I would try to answer them. So feel free to like ask questions. Guys, do you have some questions? If no, then also let me know. I mean, if am I like going too fast, or like am I like means if there are like some thing that you need me to like change, just let me know. Okay. Since you don't have like any question at this moment, I would get started with like remaining models. So model 3, as I mentioned, so it's about like the subsystem that we would need to build various ADAS and autonomous driving capabilities. And first in the line is like sensors. And in this model, we will be seeing what all sensors that we would be needing to build the ADAS or autonomous driving capabilities. So first sensor is like camera. And we need a camera because camera would be able to like capture rich semantic information. It would be able to capture like lane marking, it would be able to capture traffic signs, traffic light, pedestrians, all the object, but it would just not capture them. Means it would not just detect them, but it would also be able to provide information about their class, and the information about their category is really important because that's something would tell us how exactly these objects would move. Because let's say there is a traffic light, so I mean, just with like detection, we would identify, okay, there is obstacle next to us, and it might be anything. So let's say it's a traffic light. So camera could detect and tell, okay, there is an obstacle, but it's a traffic light. And based on that, we could say inside prediction module that that particular object would not move, and we need to observe like some different characteristics of that particular object, and that's like traffic light associated, means color associated with that traffic light. Is it like red, green, or yellow? So that's something we need to do. So the best thing about camera is like it provides like rich semantic information. Second thing, as I mentioned, it provides information about color and texture, which is essential for like this classification task later on. The next thing is about the limitations of these camera sensors. So camera sensors is something which operates on the principle or like how exactly lights is being reflected, and that's the reason it's vulnerable to poor lighting situations or whenever there is a glare, uh, or whenever there is adverse weather. So in that situation, camera sensor would not work well. So that's one of the limitation of like camera sensors. uh, but like means for each sensor there would be like certain positives and there would be like certain limitations, and that's the reason eventually we would need to do sensor fusion uh, in order to like use the best combination that would like have like lesser limitations in terms of like sensing the environment. So that's about like camera sensors, and camera sensors are essential whenever we are building this lane assist feature, traffic sign recognition, or pedestrian detection features. Means I'm just talking about like this level 0, level 1, or level 2 feature. But level 2 onwards, since at these stages, vehicle would be doing this dynamic driving task control. So in that situation, camera sensors would be like really useful and important. And there is one more like good thing about camera sensor is like camera sensor are like really cheap. Okay, so we could put like a lot of camera sensors around our car. And second thing is like there is a lot of research that's been done on vision, and that's the reason we could use it effectively these days, and that's what Tesla is doing. But that's about camera sensors. Second thing is about radar, and basically in case of the radar, the best thing about radar is like radar would be able to detect the location of the obstacles, but it would just not detect the obstacles, but based on the Doppler effect it would also be able to provide information about relative velocity of that obstacle with respect to your vehicle. Second good thing about like radar is it would perform very well in adverse weather. Means whenever there is like rain, fog, or dust, so in that situation radar would like work very well. Like this year only, like in July or so, there was like test that was conducted in China, and during that test what they did was like they put dummy in like this fog environment, or maybe like they simulated this rainfall, and they put dummy over there, and most of the vehicles were not able to detect that particular vehicle because means whenever there is like weather, adverse weather, camera sensor might not work well. But in that situation radar sensors could work well. Yeah, and that's the reason it would work, or it would detect that dummy, and collisions could be avoided, or pedestrians could be saved. The next thing about radar is like it has like really good capability to penetrate materials, and that's the reason it would be suitable for like blind spot detection activity. I guess I would be having like some slides later on where yeah. So basically, I've just like created this field of view for various sensor based on their sensor coverage. But like you could see like there are like certain white spots that are remaining around ego car, and basically these are like blind spots, and we just need to minimize them as much as possible. And that's something we could means in this situation radar would like help us very well. Like one of the bad thing about radar is like its resolution. Means you could have like really good capability to detect vehicles, but in order to get that resolution which is like really good, or where you are able to detect like really small objects or vehicles, you need to put like a lot of money over there, so they might get like expensive if you want to have like really low resolution. But the best thing about radars, and the main reason they are used on autonomous vehicles, are because their capability to detect the vehicles, to like provide distance of that vehicle with respect to ego vehicle, and to get the relative velocity. The next sensor that's been used in case of the autonomous vehicle, it's called LiDAR. And again, it's working on principle of like this light detection and ranging principle. Basically, lasers would be like emitting laser waves, laser rays, and those would be like reflected by the object in its path, and based on this time of travel we could calculate the distance of that particular obstacle from the ego vehicle. So lidars are, since lidars are using light waves and not like electromagnetic waves, um, as in case of like radar, lidar would have like really good capability to provide like 3D geometry, or like to provide information about 3D geometry of the object. So they could provide like really good information about the distance of the object, and that's the reason they are used whenever you would want to generate HD maps of the environment around the ego vehicle. uh, and based on those HD maps, or like whenever you would want to do like SLAM, that is simultaneous localization and mapping, or for precise localization, we would be like relying on lidar sensors, and then we would be using some algorithms like KISS-ICP or like some other algorithms to like localize vehicle very well, and then also generate the map of the environment. So the good thing about or pros of lidar would be like their ability to provide like precise geometry of the obstacles, or to provide like really precise distance of the obstacles from the ego vehicle. And weakness of like lidar, like first one that all know is like cost. Lidar sensor like really expensive. These days like Velodyne is like trying to provide cheaper lidar, but that's something it's just for, I guess, for academic research or like for research purpose. But the lidar sensors that are put on like ego vehicle means actual autonomous vehicles, they're like really expensive. One more limitation about lidar is also about their sensitivity to the weather. Means the one example that I could give, like let's say there is like fog. In that situation, whenever we use like lidar sensors, so you would get like these false reflections from like those small droplets in the air, and that's something would be like limiting the capability of lidar sensor to precisely map the environment. There are ways to deal with that thing, but that's like limitation of lidar sensor at this moment. uh, that's like they are costly and they are like weather sensitive. And again, in case of the lidar, we could like make classification between like this solid state lidar, where we would not be using any rotating parts, and then there would be like another class of lidar which is called like mechanical lidars, where we would be using these rotating mirrors. And yeah, these, since there are like rotating parts, there would be issues about reliability because there are chances they might fail, and we don't know when. So there is like proper maintenance that's needed, and that's something is like providing additional limitation for lidar sensor. So, and then force sensor, which is also again under the category of these extraceptive sensors, it's called as like ultrasonic sensor. And ultrasonic sensor work on the principle of like sound. So sound waves will be like sent out, and based on their reflection and like this time of travel, they would be like detecting the object and like reduce your blind spot region um, to minimal. So that's like ultrasonic sensor. It work on a principle of like sound wave reflection, and it would be able to give you like distance. That's like ultrasonic sensor. And limitation again for like this ultrasonic sensor, poor angular resolution. It's short range. Ultrasonic sensor generally would have range from 0 to 5 meter. After that, they means they would not be able to provide like that precise distance measurements and interference, basically to sound wave. So there are chances it might interfere with like other sources, and it would give like false measurements. But for like short distances, ultrasonic sensors are like really well. And that's the reason whenever they're like ADAS project related to this parking system, or like automated valet parking, so in that situation this ultrasonic sensor could be used to avoid collision with like some these barriers that are used inside parking valet, means this parking lot. But that's means camera, radar, lidar, and ultrasonic sensor. These are like four sensors that are called as like extra safety sensors, and they're called extra safety because these sensors are something which are helping ego vehicle to sense what's outside the ego vehicle. And then there is a second category of the sensor which is called like introspective sensor, and this sensor help us to provide information about the state of ego vehicle. And the first one is like this inertial measurement unit, that's IMU sensor. And inside IMU, again, we would be having this accelerometer, gyroscope, and also magnetometer. So these three sensors or like these subsystems would be like means they would be like working closely, and based on that, they would be able to provide us information about this acceleration, yaw, pitch, and roll. So that's something we would get from IMU sensor. And there are like reasons why we use magnetometer over here just to get rid of like certain errors. Otherwise, accelerometer would be enough to provide information about acceleration, and gyroscope would be enough to provide information about this angular displacement. But just to get rid of like these errors, we would be using magnetometer inside IMU. And then the next sensor, which is under category of like this interoceptive sensor, is called GNSS sensor, and that's something would be used for global positioning. So inside GNSS, we would need like at least uh, like some satellite continuously navigating around Earth, and using those two satellites as a reference, we would be able to localize ego vehicle anywhere on the Earth. But the weakness for like GNSS would be, means since we would be using like IMU over here, and like it would be dependent on these two like satellites, there are chances we might have like drifts for IMU. Second thing, there are locations where we would not be able to have like proper range for like this. Means we would not be able to connect to those satellites in the air or like in space. So those areas could be like tunnels or urban areas. In that situation, we would not be able to connect to satellites properly, and our positioning capability would get compromised. And in that situation, sometimes we might have like inaccuracy of the order of like 10 meters or 15 meters, and that's huge because we would be using IMU and GNSS for localization purpose. And like any range, means any value above zero point 0.1 meter or like 1 meter would be like detrimental for the performance of like autonomous vehicles. So that's like issue about like GNSS sensor, that like there are chances it might have like outage. But we could like work on this uplinking and downlinking frequency, and we could have like this differential like setup, and that's something would help us to deal with these issues. And apart from that, the second thing that we could try, like we could perform fusion between this IMU and GNSS sensor, and using this data reckoning, we would be able to solve these issues that we generally would have. And yeah, for fusion, we could use like Kalman filter, factor graphs, or SLAM, and that's something would help us improve the accuracy and provide localization with like reasonably good value, I would say. But still it would not be that accurate, where we could like rely fully on just this IMU and GNSS sensor. But these are the sensors that we would be using to sense the environment around the ego vehicle, and also to sense the state of ego vehicle itself. Once we have like information about this environment, that information would be in like raw format. And for example, I would just be explaining this thing with the help of like camera sensor. Whenever we use camera sensor, the information that we would get would be in the form of like images, that would be like in the form of like RGB images, and that's like raw information. It's just like these arrays, okay? And that information would not be enough unless we convert that information in some sort of like converted, or like some sort of like information where we have a solid representation of the environment around the ego vehicle. And in order to convert that raw information that we are getting with the help of like this camera sensor or lidar sensor or radar sensor, we would need to do like some sort of processing on that data, and that something would help us give us like this like process or like process tracks of the non-ego vehicle around the ego vehicle. So, for example, for this camera image, first of all, the thing that we would need to do, we would need to detect the non-ego, like we need to detect non-ego vehicle that are around the ego vehicle. But just detecting them wouldn't be enough. We also need to categorize them. And basically, detection thing is something called as like localization. Means we would be able to like localize non-ego vehicle around the ego vehicle in that image itself. That's something called as like localization. Once we add like class or category to that particular localized object, the combined two things would be called as like object detection, and object detection would tell us, okay, where exactly non-ego vehicle is with respect to ego vehicle. Once we get that information, we would need to track that object over a frame, over number of frames, and that's something would give us like track for that particular non-ego vehicle. And this information is necessary for us because once we are having like trajectory of non-ego vehicle for like certain number of timestamps, we would be able to see how exactly they would move in the future, and that something would be useful for prediction subsystem as well. But inside perception, we would be performing some sort of processing on raw RGB information that we would be getting with the help of like camera sensor. We would be doing this object detection, we would be doing tracking, and eventually we would be getting a number of tracks that are there around the non-ego vehicle. And that's like useful information because we now know where exactly non-ego vehicles are with respect to ego vehicle. And if we understand how exactly those non-ego vehicles would move in future, that's something we would be doing in a prediction subsystem. We could make decision for ourselves, we could decide trajectory for ourselves inside planning module. But that's the perception thing, means like whatever information that we are getting from various sensors, let it be camera, means whenever we get information in the form of like images, we need to perform post processing, or we need to perform like processing on that raw information in order to get like number of tracks that are present around the non-ego vehicle. And then we could just like extend that thing further to get its like future trajectories inside prediction module. The next thing is means we could also process lidar information in similar way. Same goes for like radar, and same goes for like ultrasonic sensor. And then comes means, as I mentioned, for each of those sensor, like let it be lidar, let it be radar, let it be camera or ultrasonic sensor, all of those sensors have some sort of like limitations, and those sensors are good at like some task. So what we could do, we could try to use the best part of like each of those sensors. We would merge their capabilities, and based on that, we would be able to have robust representation, or like we would have robust uh, we would have like proper capture of the environment around us, and that's something would eventually be converted into robust representation of the, or like full-fledged or comprehensive representation of the environment around the ego vehicle. So that's the sensor fusion, means fusing the information from two or more sensor in a such a way that like final output would be like much accurate than single sensor itself, or like process information that we would be getting from single sensor. So that's the sensor fusion. That's like one use that we would have uh, by doing sensor fusion. And second thing is also about synchronization. That's something we would also need to work on. But there are various ways in which like this sensor fusion could be done. And with the help of these deep learning models, it is possible to fuse the information from camera and lidar and radar in raw form itself. So that's like one capability, means we would just take like these RGB images, lidar point cloud, radar point cloud directly, and we could feed them to deep learning module, and eventually we would be getting like final number of tracks from for like that particular scenario. That's like raw database sensor fusion. Second thing is the feature level sensor fusion. So in case of the feature level sensor fusion, what we would be doing, we would not be detecting like ego vehicle itself, but we would try to detect some signature inside camera image, or inside lidar point cloud, or inside radar point cloud. And then we would try to merge those feature level signals uh, inside like further pipeline. So that's like feature level sensor fusion. And then comes object level sensor fusion. Object level sensor fusion is the one where we would be detecting vehicles inside camera image, we would be detecting vehicles inside lidar point cloud, and we would be detecting them inside radar as well. And then we would be merging those outputs or measurements, and then based on these Kalman filters or like some other filter that we could use, uh, we could have means extended Kalman filters, or we could have like particle filters. So based on that, we would try to have like more accurate representation of the vehicles around us. So that's like sensor fusion for you guys. So means until this point, what we have done, we have looked at like various sensors that we could use for autonomous driving. Then we have seen why do we need to do sensor fusion. because some of those sensors might have like some limitations. So just to get rid of those limitations and to have better representation, we would be doing sensor fusion, and we have seen like various ways to do that sensor fusion. And we have also briefly seen how exactly we could do perception, or how exactly we could process the information that we would be getting from individual sensor. Let it be camera image, let it be lidar point cloud, or let it be radar point cloud. That's the perception. Now we have arrived at that point where we are getting tracks for all the non-ego vehicle around ego vehicle. Okay, but the important thing is that like means whenever we are like tracking this object, it's just not the single object that we would need to track. We would need to track multiple object at once, and that itself is like really humongous task. And to solve that particular task, we would need to come with like some algorithms, and that's something we would be seeing inside this tracking and data association. And this one particular module would be really useful to you guys whenever you try to build this ACCAB pipeline or LK pipeline, because in real world we would not be just like tracking single vehicle, rather we would be tracking means 15, 16, 20, or 25 vehicles at once. So we really need to understand how exactly we could perform this multi-object tracking. So that's the thing that we would need to understand, because this task itself is like really difficult. And like the major issue that might occur are like occlusion. Means a vehicle is like seen for like certain number of frames, and then it is being like occluded by other vehicle, or like means is being not detected, or there are like false detections. uh, yeah, sensor noise, and then ID switches. So there are like certain challenges are there, and that because of these challenges it's really hard to do multi-object tracking. And it means during this course I would try to show you like two projects. One is about like this bicycle tracking, and when I show that project you would understand, okay, means when we have like single object detection done, and whenever we are trying to track it, it's really possible to do that thing just with the help of like Kalman filters. But whenever we try to switch that thing with real world scenario where we have means 20, 25 non-ego vehicles around ego vehicle, in that situation just using Kalman filters and like this means object detection with the help of YOLO followed by Kalman filter would not be enough. We'd need like much better paradigm, and that's something we would be getting inside this multi-object tracking framework. uh, and the additional thing that we would need to add over here is like capability to do data association. And there are various ways in which it could be done. So this joint probability data association is like one of the like best algorithm that was there in 2019 or 2020 for like this data association purpose. But right now people are just doing it means with the help of like deep learning. Means there was like there is like this algorithm called like sparse 4D. With the help of this algorithm you could do this multi-object tracking very effectively without you having to use this Kalman filters or like this association algorithm separately. But the major thing that you would be doing again would be similar to that Kalman filter. You would be initiating those tracks, you would be maintaining them, and you would be deleting them if they are not visible. And while doing this, you would also need to take care of like this association between various measurements that you would be having. Association between the tracks that you would be having at time frame means t equal to 0, and the detection that you would be getting at t equal to 1. So you just need to work on this data association, and once you are able to solve this problem, you would be able to do multi-object tracking very effectively. So this is important thing, and I just wanted to briefly introduce this thing over here so that you would understand. It's just not like simple pipeline where you just detect object, you track them with the Kalman filters, and then eventually you get like all the like track that might be there around ego vehicle. Rather it's like more complicated in real world because of these challenges like occlusion sensor fusion. So that's like multi-object tracking. The next thing is, I guess we have one more slide. It's just like better visuals. But yeah, what means I mentioned why are we doing sensor fusion, because all the sensors that we are using, some of them have like means they have like some pros and they have like some cons. But if you would want to use if you just want to use like single sensor, then we might not be able to do, or we might not be able to represent the world in it in full accuracy. So that to avoid that thing, what we could do, we could try to merge various sensors and by merging that information, we would be able to add like redundancy, and that redundancy is something leading to the safety. So that's the reason we do sensor fusion. Yeah. And yeah, over here, like it's just like simple example, a camera, then like point cloud from the radar and lidar, and each of these three sensors have their like own advantages. Like for camera, we would be able to get like this highly semantic information, means high semantic information, or like precise semantic information that we would be getting from camera images. From radar, we would be getting velocity and distance, and it would be like working well in all weathers. And then from lidar, we would be getting like precise 3D geometry. So we would be like putting together advantages of like these three sensors. We would be feeding them through like this fusion pipeline, and then eventually we would be getting like robust environment model, where we would understand what all means, what would be the position of all non-ego vehicle around ego vehicle. So that's like sensor fusion that we would be doing inside with this multi-object tracking paradigm. So that's like model 3. So until this point, what we have done, we have sensors which would help us to like detect the environment, means all the vehicles or like all the obstacles in the environment. Then we would be able to track them over a period of time, and then based on this multi-object tracking or association, we would be able to identify, okay, what are the final trajectories that would be there around ego vehicle. So we have like number of trajectories around ego vehicle, and based on that, what we would want to do inside model 4, we would want to first of all understand how exactly those trajectories that we have at this stage of like this sensor fusion, how exactly those non-ego vehicles would move for like next 2 or 3 times. So that's something we would want to do inside prediction. The next thing, once we understand how exactly those vehicles would be moving, we would be doing planning, and then we would be coming up with our own trajectory to avoid those non-ego vehicles, and to follow our like goal. And eventually we would be like coming with the trajectories, and then we would be calculating control signals to follow those trajectory. So first thing is like prediction, and there are various ways in which this prediction thing could be done. First one is like physics-based kinematics models, or like basically we call them like motion models. And using this constant velocity motion model, or like constant velocity means constant acceleration motion model, uh, or like there are like 2 or 3 other models are also available. So using this motion model, we would be able to tell, okay, what exactly would be future position for that particular non-ego vehicle up to 2 times or 3 times. So that's like physics based or motion model based prediction of the trajectory for non-ego vehicle. Second thing is like probabilistic models, like this naive-bayes algorithms. So over there, we would be like weighting like various outcomes that we would be having, and based on the measurement that we would be having for like next timestamp, we would be assigning more weights to like particular trajectory, and we would be saying, okay, non-ego vehicle would might follow this particular trajectory, where we have like possibility of like 60%. So we would say, okay, non-ego vehicle would follow this particular trajectory, or this pedestrian would follow this trajectory, because at this one time stamp t equal to 0, uh, means we are running like this Bayesian algorithm, and then we get like next measurement, and based on that next measurement, we say, okay, it seems like this pedestrian is like going in this direction, so this particular trajectory would have like higher probability of occurrence. And that's like probabilistic model that we have over here. Okay, and basically we could do this thing with the help of like Naive-Bayes algorithm. And like in our case also, like we did publish one paper back in 2021, and it was about how can we improve capability of this Naive-Bayes algorithm. Basically we try to merge these two approaches, motion models and probabilistic models, and based on that we were trying to improve capability to do prediction in much better way. But nowadays, like there are like various deep learning based approaches are available, which are helping us to predict the future trajectories of like non-ego vehicles very well, and they would be like relying on huge number, means huge amount of data, but that data is like already available inside Waymo dataset or Newson dataset. And using that data set, we would be able to train neural networks or like deep learning model in a such a way that we would be able to like predict future trajectories for like some timestamps uh, accurately. So that's something we could do. But with this prediction, what we could understand is like how exactly non-ego vehicle would move for like next few times, and that's really important because we don't want to plan whenever we plan trajectory for ego vehicle or like vehicle that we are trying to make autonomous. We just don't want to plan trajectory for like current timestamps, but we would want to plan trajectory for like next 10 seconds or like 15 seconds or maybe 1 hour. But that's like really long time. But this is like behavior level planning that we do, and over there we need to plan at least for like 5 seconds or 10 seconds. And in that situation, having information about non-ego vehicle trajectory in future makes like a lot of sense. So having information or like having prediction model running is like must in order to plan trajectory for ego vehicle. So now we know what is the position of like non-ego vehicle around ego vehicle in terms of tracks. Means we know where exactly that particular non-ego vehicle was for like t equal to -1, t equal to -2, and we also know where exactly that particular non-ego vehicle would be at t equal to 1 or t equal to 2 seconds. Now we need to plan our own trajectory. That's the trajectory of the ego vehicle, and for that purpose, means we could like rely on game theory based approach, or we could also rely on this hierarchical decomposition based approach, where we would try to decompose the task of this planning into certain stages, and we would be performing those tasks. So for planning, we could perform mission level planning, and inside mission level planning, basically what happens, we would just come up with like path to start, means path from like source point to the destination. Let's say we would want to move from like one city to another city. That planning would be done inside mission planner. It could be with the, like this A star or like other algorithm that we would be using, but that would be mission planning. We would just be getting like this high level path from like source to destination. Once we get like this high level path, it could be like for, means we would be having horizon for each of these planning tasks. Whenever we're talking about like mission planning, means whenever we try to get like path to move from like one city to another city, it could be for like hours. But the next thing is that like having that path is useful. That something would help us what exactly, means what path we would need to follow. But now we need to reduce the time horizon for decision making, and this is where this behavior planning comes in. And behavior planning would help us to make a decision for like time horizon of like, let's say, 5 second or 10 second. And inside behavior planning, what we would be doing is like we would be making decisions like, should I go straight, should I move to left lane, should I move to right lane, should I brake, should I stay idle at intersection, or should I accelerate. So all those decisions will be taken inside behavior planner based on the information that we are getting from perception, sensor fusion, and prediction module, also from localization and mapping module that that we would be having running parallelly. So that would be behavior planner, which would have like time span of like, or time horizon of like 5 second or 10 second. Once we have like high level trajectory or high level path from like one city to another city, that's mission planning. Inside that time horizon of like 1 hour or 2 hour, we would be having behavior planner that would be for like 5 or 10 second. Now we know, okay, we need to move to left lane or we need to move to right lane. So that's the behavior plan that we have for 5 seconds or 10 seconds. But once we have like that behavior plan for 5 seconds, what we need to do is like we need to come with a trajectory, actual waypoints that ego vehicle would be following. And this task could be like split into, means traditionally it's something like being means being classified or not classified, but it would be categorized into two parts. So we come up with like trajectory separately, and then we come up with like velocity profile separately. That's the trajectory planning. And then nowadays people, means not nowadays, but for like last few years, people are also using MPC to do trajectory planning and control simultaneously, because that way you would have like better control over the objectives and constraints. So that's the planning thing. Now we would try to understand the mission planning. I have already explained that thing, but inside mission planning, what basically we do, or what all tasks that we would need to do, like we need to determine the destination, we need to find our source point, and then using various algorithm, it could be like a Dijkstra, it could be A star algorithm, or like means Bellman Ford. So we would be like coming up with like path from like source to destination, and we would be assigning like various constraint on our path. We would be associating various costs to that, and based on that we would be choosing that path which would be like really efficient and like optimal. So that's the mission planning, and that would act as a reference path. Once we have like reference path that would have like time horizon like 1 or 2 hour, we would be doing behavior planning, which would be valid for like 5 to 10 seconds, where we would be making decisions: should I go straight left, should I move to left lane, right lane? And after behavior planning, we would be means whenever we are doing like behavior planning, there are like a lot of constraints that we would need to consider. But yeah, you could also think about them. Means I would share this PPT with you, but these are like some supervisory things that you would need to do at behavioral level. Like, do I need to means does a vehicle need to go into fallback situation where driver need to take control or not, or means are we really going inside our designated ODD or not? Means so basically we need to think about all these safety parameters inside behavior planner, and based on that we need to make a decision: should we allow system to take control over a vehicle, or should we delegate that control to the driver? So these sort of decisions we need to make inside behavior planner. And then inside trajectory generation, as I mentioned, it would have like time span of like 1 to 2 or maybe 5 seconds, and we would need to come with like actual trajectory. And whenever we are like coming up with a trajectory, we would have like various constraints. We need to ensure that like the trajectory that we are having should be collision free. That trajectory should be such that there should be like no jerks. Then this like lateral acceleration and other parameters should not be there in huge quantity, and it should be smooth. And there are various ways in which you could like come up with that trajectory. Okay, so yeah, means for like this undefined or like unstructured environment, you could use RR star algorithm, and for like other general task, you could use MPC, or you could use like chomp. So these are the algorithm that you could use, or you could also simply use like these polynomial spines. Means it could be like quintic polynomials. Means quadratic would not work well. And but yeah, means in our case we did use like quintic polynomials, and we were able to get like really good trajectory, and that was able to meet our requirement, where we were able to minimize the jerk, we were able to respect the vehicle kinematics, these holonomic constraints, and also we were able to get smooth trajectory. So we need to consider all these constraints, and we need to come up with the actual trajectory. And once we get this trajectory, like means we cannot have this infeasible path that's shown in red. The path that's shown in this dotted line is jerky one. So we need like this smooth trajectory, which would which vehicle could follow efficiently by respecting its holonomic constraints, where we would have like minimal joke, and there is no collision with like non-ego vehicles. So we need to come with that trajectory, and then we need to decide about the actual velocity profile. And once we have like these two things ready, actual path and velocity profile, we could feed it to like control system, or like control module. And that's like final thing, means we have perception, we have prediction, we have planning, and then finally we have control module. So inside control we need to think about two things. Means in case of the ADAS, or in case of autonomous driving, there are like two things that are important. First is about like controlling the longitudinal dynamics, controlling the lateral dynamics, and these two things are enough to make sure like vehicle is following particular trajectory. But obviously we would also need to think about this vertical dynamics, suspension system, and other parameter. But in case of the autonomous driving, having just control over like two of these dynamics would be enough. And for longitudinal control, as I mentioned, we would be coming up with actual velocity profile, we would be coming up with trajectory. So we could use like this simple PID controller, we could use like this quadratic regressor like LQR, or we could be using like this adaptive MPC. And based on that, we would be able to control like or we would be able to have like particular velocity profile for our vehicle. So that's like longitudinal dynamics. And then that's something called as like longitudinal control for ego vehicle. And then there is a lateral control. And in case of the lateral control, what we do, we would try to make sure our ego vehicle would follow particular that path profile. So that actual trajectory that we are getting from this trajectory generation thing, or like local planning module, we would try to follow that. And then again, this lateral controller that we have with us, they are like geometry based, and some of them are like dynamic based. So pure pursuit controller or like Stanley controller. So these two are like really good one, because over there you don't need to worry about dynamics of your vehicle. But again, if you are not considering dynamic, that means you cannot use like lateral controller at really high velocity. And whenever like vehicles or like cars are moving at higher velocity, in that situation you could use MPC, or you would need to use MPC for lateral control purpose. And yeah, final thing is like whenever we are building this longitudinal control or lateral control capability, we need to make sure that like those things are like integrating really well with this anti-lock braking system, or this electronic stability control module, or traction control module, or like other systems that are there. So we just need to make sure that integration is happening well. And if we are able to do that, then what we could do, like we would be able to follow reference path that we are getting from mission planner. We would be able to implement the immediate behavior that we have planned inside behavior planner, and then we would try to pursue the trajectory that we are getting local planner as closely as possible. Not 100%, but we would try to follow it as closely as possible. Oh, yeah, and that's something we are saying. Okay, we are just trying to minimize the tracking error that we are getting inside this lateral controller. But with this, with perception part, prediction part, planning part, and control part, we now know the entire pipeline that we would need to implement either ADAS features or autonomous driving capabilities. And now we would need to, now we would like have a look at like certain case studies, so that you would understand in order to build this particular ADAS feature, how exactly all these subsystems are like coming into the picture. So first is like this automatic emergency braking system. So in order to implement this automatic emergency braking system, the first thing is like you would need sensors. So you would need camera sensor, you would need radar sensor, you would need lidar sensor. The major thing that we would want to do over here is like we would need sensor, and we need sensor because we would want to detect the vehicle that's next to the ego vehicle, because that's when this automatic emergency braking system would come into the picture. Because one more thing that we need to understand over here, uh, and that's something would be considered like stakeholder requirement. Stakeholder requirement could be that like means whenever there is an obstacle next to ego vehicle, our vehicle should comes to standstill. So if that is the condition, or if that's the requirement that's posed by stakeholder, so in that situation, what we need to do, we need a capability to detect the non-ego vehicles or like obstacle next to ego vehicle. So we would need to detect it, and in order to detect it we would need like proper sensors. So we need to see like where exactly we would want to implement AEB. Means based on our like precision and accuracy that's demanded of a particular feature, we could just use like camera, we could use radar, or we could use lidar, or we could use like all of them. So that something is needed. Once we do detection, the next thing that we would need to do is like we need to calculate this time to collision. A time to collision is a time that basically it's the time that ego vehicle need in order to collide with non-ego vehicle. So we need to calculate this time to collision, and then we would be comparing this time to collision with certain threshold, that's like a braking distance and braking time that we would need. And based on that, we would be first of all warning the driver, that's like forward collision warning. Then we if driver is taking cognizance of that thing, it's fine. If he's braking, that's fine. If driver is not braking, then we would do like partial braking, maybe like at 1.5 or maybe at like 3 meter per second square. But if driver is really not taking any cognizance, he is really not intervening, in that situation we would be having like full braking, maybe at like 5 meter per second square. That's like means huge value, but we would be having like full braking. And we would try to stop the vehicle in such a way that collision or like damage from the collision is like minimized. Means either collision is avoided, or like damage from the collision can be minimized. So that is the automatic emergency braking system. And like major subsystems that are like being invoked over here is like we would need like proper we need sensors, we need a perception, we need sensor fusion, we would need we don't need like prediction over here, but if we integrate prediction, then that's fine. We don't need actual planning module that I just explained: mission planning, behavior planning, and local planning. So those sort of things are not needed inside time to collision thing. But we just need like perception, we need uh, sensor fusion, and then we need control part. So if we have like this subsystem available with us, then we would be able to implement this automated emergency braking system, and we would be able to stop the vehicle. And means it's been shown with the help of like some empirical data that it would be able to reduce number of collisions by 40% or more than 40%. And most of, means the major contribution for those crash reduction would be coming from like these rear end collisions that are being avoided, because that's what ego vehicle is doing. It's trying to stop itself whenever there is vehicle next to it. So it's reducing rear end collisions. The next thing is like challenges for AEB, but again those are not challenges. It just about like limitation that we have in terms of the sensor that we use. Like nighttime camera would not work well in nighttime, but we could use list because in case of the radars, they would not have like that good resolution. Means if the resolution is high, they would not be able to detect pedestrian cyclists that well. So we would need to make sure that like radar would have like really low resolution, and then they would be able to detect pedestrians and cyclists very well. Again, in case of the pedestrians and cyclists, and these particular actors are like really having like uncertain trajectory, so that could again be a challenge. But and yeah, actually according to NCAP, this is one of the standard that's being used in industry, and they have mandated that like all the vehicles should be having AAB installed on it before it goes out on the roads. And like means all like regulatory bodies have given certain timeline for that, but AAB is like at the top of the list in terms of like their means they are like really warranted in case of the commercial vehicles or cars. So that's automatic emergency braking. The reason I'm showing this case studies over here, just to highlight, whenever means water pipeline that I showed you, perception, prediction, planning and control, all those subsystems are not needed whenever you would want to build feature like automatic emergency braking system. Because in case of the automatic emergency braking system, you would just try to have control over longitudinal dynamics of your vehicle. That's like L1 capability. Then comes like this adaptive cruise control. In case of the adaptive cruise control, your objective would be you would try to maintain the velocity of your vehicle at certain speed, uh, as long as like it's driving normally on highway and there is like no imminent collision or no non-eco vehicle present next to it. And whenever there is a car next to it, it should be maintaining certain distance from that. So it would have like two modes: headway control mode and the constant velocity mode. And in order to implement it again, we don't need planning module. We just need like this perception, sensor fusion, multiple tracking maybe, and we need like this control module and specific logic for ACC. But we really don't need planning module. And again, since we would be like talking about velocity, just having information about like object location would not be enough. We would also need to measure its velocity. So we would need a combination of like radar and camera. And as I mentioned, ACC would like provide comfort to the driver. So AEB is like more about safety, but ACC just not about safety. It's also about comfort. Means as long as it's operating in headway mode, it could be considered as like safety feature. But as means once it moves into this constant velocity mode or will this cruise mode, it's all about comfort. It's just like reducing the effort that driver would need to put to maintain the velocity of the vehicle. So that's the adaptive cruise control feature. And these are just like some snippets or like snapshots from the actual module. Means whenever you build like this AEB and ACC feature, you would be having like something similar architecture. So you would be like taking certain signals like relative distance, ego velocity, driver signal, and TTC, and based on that, you would be calculating signals for like acceleration and braking, and yeah, those signals would be given downstream. And yeah, the next thing is like lane keep assist feature. So in case of the lane keep assist feature as well, you would just need like information about camera. You would not need radar over here. And then you would need means you would need perception. You would need sensor fusion. No, actually you don't need sensor fusion. You just need like perception, and you just need like control module. Okay, for lane keep assist. Yeah, so that's like simple case study that you have. But because of lane keep assist, you would need to have like some sort of like capability or like means you need to have like some sort of mastery or like state flow, because in case of the lane keep assist system, our vehicle would be operating in like various states, and based on that, you would need to turn on certain signals or like you would need to implement braking and like means you would just need to implement that thing in better way. So yeah, means whenever you work on LK feature, you would understand that thing well. But yeah, means you would need like some mastery or like state flow for that, because you would be means basically you would be using state machine for this purpose. You would be having like various states for your ego vehicle, and you just need to have like proper decision making capability, and state flow is like really good with that. But these are like some basic case studies, yeah. And once you build like this particular feature, you would need to test or you would need to validate that it's working well. Means not just like in one single situation in simple straight road, but on like curve road as well, it should work well. And this particular snippet is from like our another paper that we published onto SAE in 2022, where we try to combine Stanley controller, like the Stanley lateral controller, with a perception module. So basically, we detected lane markings and some sort of like prediction module is something we added, and based on that, we were able to achieve really good performance. So we like publish our findings to SAE in 2022. So that's like module 4. And in module 3 and module 4, what we have done is like we have understood like entire pipeline that we would need to implement, or we would need to build ADAS and autonomous driving capabilities. Now in module 5, we would try to understand how exactly we would build them, and what's the relevance of like system engineering over here, how exactly we could build them with the help of like V diagram, and how can we validate them with the help of like this mill, seal, and peel and hill testing and other like approaches. And eventually we would talk about standards. But before going to module 5, I would like to understand, or I would try to take a pause for a bit, and I would try to understand, are there like some questions? Guys, if you have any questions, just feel free to ask them. Okay, I'll try to answer them.
Hello.
Yeah.
Yes, sir. I'm Karan Jalwani. Sir, you mentioned that Rost also there.
You can
And
call me Mayur. Please don't call me sir. I'm really tired of this thing.
uh,
Please.
uh,
I'm sorry
yes,
for that. But yeah.
sir, you use Rost there and
Sorry.
MPC also MATLAB and Rost too. Robotic
Mm-hmm.
operating system too. Then how to interact? Is it possible to interact ROS too, like Gazebo platform with MATLAB
Yeah.
for
So thing is
simulation
that like,
purpose?
yeah, yeah. So there are like two ways. So first thing is like whenever you try to implement this pipeline, so you would be using like the simulation buses. Okay. So this buses is something you would be using inside Simulink environment. So they would means those buses would be simulating the signal that would be passing through this middleware. That's the first thing that you would be using, simulation buses. But do they means you could just use them to pass the signals, but they would not represent the actual physical entity. And this is where you could use like ROS. So inside like MATLAB and Simulink environment, you do have this ROS2 like module available, or like this toolbox available. So with the help of that, you would be able to add like ROS2 nodes for each of that subsystem that I mentioned. And that's how you implement it actually. Whenever you build like this actual autonomous driving pipeline end to end, with this modular approach, where you have like this perception, we have prediction, sensor fusion, planning, and control. So you would be running them as like separate ROS2 node. Each of these things would be running as a separate ROS2 node, and then you would be publishing those signals to certain ROS topics, and then some nodes would be like subscribing to like certain signals, and based on that they would be doing processing, and eventually you would be getting control signals. So to answer your question, inside MATLAB and Simulink, we have a capability to use Simulink bus, and we also have capability to use like ROS2 like nodes. But like what I have seen, like people generally means it's easy to use like those ROS2 nodes, but I really don't get that feel when I use those ROS2 nodes. So I prefer to have this system, means where we could like implement this entire thing inside Linux environment with like these ROS2 nodes are like coded in C++ and Python. uh, and that's something I would be doing like in next lecture. But for this particular course, I would be doing this thing means entirely inside MATLAB and Simulink environment with the help of like Simulink buses to pass the signals from one model to another model. Did I answer your question?
Yes, sir. Yes, sir. Okay. Thank you, sir.
Yeah, thank you, Karan, for the question. Yeah. Guys, do you have like some more questions? Okay. Yeah, they are just communication protocols, but yeah, just to pass the signals means, yeah, inside autonomous vehicles we would be using like this basically in case of the autonomous vehicles we would be using ROS2, but in case of the ROS2 the issue is it's really not that means it's not suitable for the safety critical means application. For ROS1 that was the situation. ROS2 is like much safer as compared to ROS1. So currently people or like organizations are using it, but still they are like preferring to have like this traditional routes where they use this adaptive autosar or like some other middlewares. But that's the thing. Yeah. Did I put it inside middleware range? Yeah. Sorry for that. It just to like show, I mean, I wanted to put like ROS2 and ATOSR over there, but yeah, CAN and Ethernet, yeah, you are right. These are just like communication protocols and they are really not needed to be put inside middleware thing. But I just wanted to like show, okay, in order to pass these signals, we would need like some sort of channels, and we could use like this medias over there. Okay. So if you have any questions, then we could like continue. If otherwise means I would answer. If not, then I would continue with like model 5 and model 6. Do you have questions? Okay. So the next thing in module 1, module 2, we understood like motivation. Why do we need to learn about ADAS autonomous driving? Module 2, we learn about like vehicle safety, what all things it contains. Module 3, module 4, we learn about like this entire pipeline. And module 5 is all about how exactly we could build it. Because whenever we try to build something that's complex, it's really not easy, or it's really not wise to build it directly. So we could follow like some approach that's been like used for like decades, that's like system engineering. So in case of the system engineering, what we do is like we try to split the system into like smaller subsystem, and then we try to build these smaller subsystems, and then we put them together, and eventually we would have like systems of systems, and that's like final complex system. And if we follow this approach of like disintegration and composition, we would be able to keep like error, or like we would be able to contain the error quickly. So that's the reason we are using this system engineering or model based system engineering in our approach whenever we would want to build like this complex system. And another thing about like this model based system engineering is that like it provides like really good way to test our systems. Whenever we build them, we would be able to test them as well. And like one approach that's been used is like this V model. And in case of the V model, what we do in left wing of that V model, we are trying to build the this particular ADAS or autonomous driving feature, and in right wing of that V model would help us to verify and validate that particular feature. So always we would start with like stakeholders requirement, and those stakeholder requirement would be like means layman's language, and we need to convert them into like proper functional non-functional requirements. We need to perform like a proper safety analysis of that, and then once we get like proper requirements with us, based on like these systemal diagrams and like various combinations, we would need to build high level system design. And once we get this architecture ready, we could like split that into subsystems, and then for each of that subsystem we could build that module. So we would be able to build that module or design that module. And once we design that module, we could perform means at this stage only, at this stage of like this model design, whenever we have that particular thing ready inside Simulink environment or like a MATLAB environment, we would be able to perform this model in loop testing, or like we would be able to perform like software in loop testing. And once we are like done with these two things, what we could do, means code generation with the like Simulink coder or embedded coder and like other tools that we could use generally in industry. And then we could perform like processor in loop testing, and then we would integrate all these subsystem together, and then we could perform this hardware in loop testing. Once hardware in loop testing is working fine, we could go further and we could perform like this vehicle in loop testing, that's like system testing level. And then eventually we could perform like track level testing, that's acceptance testing. So left part is all about like implementation or building that ADAS feature, and second part, right wing, is all about validating or verifying that particular feature. And like means whenever we start with requirement, there would always be like two branches. One is about like system design, system development, and another branch would be about verifying or validating that particular feature. So that's the V model. The next thing is about simulation environment. because as I mentioned, inside MATLAB Simulink or the pipeline that I mentioned, we start with perception, where we do like sensor fusion, prediction, planning, and control. This entire pipeline is good enough, and we would be able to like build means we could start with like sensor signals, and we would be able to like generate signals for like our vehicle, like throttle, brake, and steering angle. But this is something we cannot do with like real vehicles, because there are like a lot of issues with that, and there are like a lot of risk involved. And to avoid those risks, what we do, we try to create like virtual worlds or replicas of the real world. And inside that replicas, we try to create like a traffic similar to real world. And that's like simulator, that's something called as like traffic simulation. And second thing is, we just don't need to worry about, or we just don't need to concern about traffic simulation, but we also need to concern about the sensor simulation. Whenever we are like simulating sensor, we need to make sure that like there is a realism inside that sensor simulation. We are able to have like proper noise models for each of those sensors. And when we like put together this traffic simulation and sensor simulation thing together, uh, we would have like this virtual world which we could use to validate or verify our ADAS features. And apart from this traffic simulation and sensor simulation, we would also need to simulate one more thing, and that's the vehicle dynamics. That's something we would be seeing, maybe no, we would be seeing it over here only. So we just don't need to simulate the traffic, we just don't need to simulate the sensors, but we also need to simulate the vehicle dynamics, because as I mentioned, we don't want to go into real world in order to get the real world data and then build this pipeline and then give actual signal back to the vehicle. Rather, we would want to create replicas of like the traffic, we want to create replicas of the sensor signals, and then we would also want to create replicas of the vehicle. So in case of the vehicle, we could like means we could like create a model of like vehicle. Means it could be like 3 degree of freedom model, or it could be like 7 degree of freedom model, or it could be 14 degree of freedom model. So that model is something would be there, and that something would help us understand how exactly vehicle would move, behave once it receive like those three signals, like throttle, brake, and steering angle, and like other excitation as well. But apart from that, we also need to think about the tire models. So it could be, did I mention those things? But yeah, Pazika tire model, or like other tire models, or like maybe wire mesh model. So we also need to think about that high fidelity tire model, so that we could simulate that suspension and tire forces very well. And once we have like all these things ready, and once we have like models for all of these things, uh, we could like simulate traffic, we could simulate sensor, we could simulate vehicle, and then we could like connect that thing to the actual pipeline that we built for ADAS or autonomous driving, and we could validate that thing or verify that thing in end-to-end fashion inside the simulator. And there are various tools that are available. Maybe we could use Carla, we could use Priscan, we could use VTD, Sumo, Roadrunner, or CarMaker. And as I mentioned earlier, I also mentioned that whenever we would want to generate simulation, we could rely on these various databases where like this accident are like registered, and based on that we could generate scenarios. But if not, we could also do like ODD based analysis. That's something like my current firm is doing, like at Deontic we are doing that. We are doing like ODD analysis, and based on that just one analysis, we would be able to generate like all that 4,000 5,000 scenarios that we would need to validate that particular ADAS feature. So that scenario generation is something I was talking about. And yeah, in our case, we would be using like IPG car maker. We could also use like vehicle dynamics toolbox from MathWorks. But in our case, we would try to go a little bit ahead, and we try to see how can we integrate like IPG car maker in our pipeline, so that we could have like high fidelity vehicle dynamics considered. But once we have like all these things available with us, what we could do, we could like simulate this pipeline in end-to-end fashion, and we could verify and validate this ADAS or autonomous driving feature. One more thing is, as I mentioned, like in our case, we would be using IPG car maker. So inside IPG car maker, you could also generate like this traffic simulation. So you could also generate scenario, and you could also choose a vehicle that you would need for your purpose. And from this IPG car maker, we could send signals about sensors to this environment, MATLAB Simulink environment. Inside MATLAB Simulink, we would be doing this processing, perception, prediction, planning, and control. And those control signal would be sent back to the actual vehicle dynamics model, and that vehicle would be like driven inside that environment. So this flow would be there, and this particular setup is called as like co-simulation. Uh, So right now for IPG car maker, there is like this means they do provide like extension for Simulink, but if there is a case where we do not have that means extension available, so in that situation, what we could do is like we could just use this functional mockup interface, which is like a framework or like which is yeah, it's a standard that's being used to exchange the models. And then there is this functional mockup unit is something we could use, means for the simulation moment and for vehicle dynamics we could create like FMUs and we could directly connect them to this MATLAB and Simulink model. So that's like one thing that's possible. And yeah, so in like later lectures we would be like seeing more about like FMI and FMU for co-simulation purpose. But for now, just to give you like idea, in our case, once we have capability to simulate the traffic, once we have capability to simulate the vehicle dynamics, simulate the sensors realistically, and capability to simulate tire model, we could like in principle containerize that thing as like single unit, and that unit could like talk to MATLAB Simulink based ADAS or autonomous driving feature, and then we could just verify and validate that thing. So that's like good thing about this core simulation. And it's just not about IPG CarMaker and MATLAB Simulink, but rather there are like multiple combinations that could be possible, maybe with the like DSpace or other providers. But this core simulation is like really good idea that we could use to get like verification and validation done quickly. Uh, the next thing inside autonomous driving is that like means I mentioned that like means whenever there is a system engineering, we could build complex system by disintegrating like bigger system into smaller systems, and then we could build smaller system. And whenever we have like smaller system, we could perform this unit testing, we could like put them together, we could perform integration testing, and eventually we would be having like the system level testing or like vehicle in loop testing. But this sort of setup is something would not work directly very well for autonomous driving. And the reason for that is like there would be just like a lot of variables that we need to consider. Okay, so it would become like really infeasible to create that many number of test cases. And that's the reason what people are doing. And that's the reason this scenario based testing framework is like really famous inside autonomous driving community or like ADAS community. Is basically inside scenario based testing, what we do is like we try to create like scenarios that represent like various driving situations, mostly like edge cases. And then we try to like drive our vehicle in that scenario. And if our ADAS feature is like working well in that situation, then we could say okay, our ADAS feature is like verified and validated. But thing is that like we are not writing a test case individually for our like particular code block or like something like that. Rather we are like uh, observing this behavior as a whole, and that's the scenario based testing. So over here the snapshot that I have added, basically this is just for like this FCW feature. As I mentioned, NCAP is something has like documented like a lot of scenarios that we could use for testing or verification and validation purpose. And I took like one scenario, and based on that, I was able to perform this verification and validation for that. So yeah, this is something you would be doing later on as well. But this is something called as like scenario based testing. I would recommend, or like means I would recommend you like you just go to web and like search for like more on like scenario based testing, and you would come across like a lot of papers. But scenario based testing is a way to verify and validate the ADAS or autonomous driving features. The next thing is like means when we want to means now we understood V model is something used to build autonomous or ADAS features. Obviously the pipeline would remain same: perception, prediction, planning, control. But like V model or model based system engineering is like way to build it. uh, Next thing is like to verification and validation. We cannot just use like this normal setup that we generally use inside software engineering, where we write like unit test, integration test, or like regression test, or like other test cases. But we need to go further, and we need to rely on like scenario based testing. And once we do like this scenario based testing, uh, we need to like perform like certain tests over there. Okay, so we would be doing like this mill testing, that's like model in loop testing. We would be doing like software in loop testing. So and then once we are like sure about it performance, we would be generating code, and then we would be putting it on like process ECU. And then our civil we would combine that with like simulation environment, and we would be performing like processor in loop testing. And once that thing is done, virtual validation is done. Next thing is we would need to like put vehicle control, or like means a controller that we have developed for like ADAS features on like one issue, and then we would need to put like this entire simulation environment on like another issue, and we just need to like create interface between them, and that's something would be considered like this hill testing. Okay, so inside hill testing we would be able to identify like means we could perform like this various cybersecurity test, we could do like fault injection, and we could try to understand what all issues that might occur whenever we are trying to connect all these subsystems to each other. So that's like hill testing, hardware in loop testing. And once we are like through this integration test, we could perform like vehicle in loop testing, means we could like take our ECU that we tested with hill, and we could put it in a real car, and then that real car would be driven around particular test track, and that's how we would be performing this vehicle in loop testing, and that's like system level testing. And then eventually we would be doing like this acceptance testing. And as I mentioned earlier, that we would be looking more into this FMI and FMU later on. So this is like simple setup, or like this is diagram that I found. But when I was like working at FEV, I did work with like the space part, and like this setup is quite similar. So I could just like vouch for like accuracy of this diagram. That we have like this control desk, model desk, and motion desk. All of those things are available inside desktop, and these tools are like provided by DSpace. And then we would be like getting those tools, we would be creating like this FMUs for that, and those FMUs would be like integrated with our, means those FMUs would be like loaded separately on separate issues, and we would be performing this hardware in loop testing eventually with the like this DSpace Scalexia environment. And means now we have understood inside model 5 how exactly we could build ADAS or autonomous driving feature with the model-based system engineering, and how can verify or validate them. Now next is about model 6, and model 6 is about functional safety and standards, because I did mention that it's a complex system, it's safety critical system, and in order to put this system on a road, we would need to put a lot of efforts uh, into making sure like this system is like really reliable, and people should have like proper trust in this thing. And that's the reason whenever we are writing down requirement, we perform like proper testing, and that testing should be in consistency with like proper standards. And for functional safety, there is standard that's given by ISO, that's like 26262. That's the functional safety standard. So inside functional safety, we have like this proper pipeline or number of steps that we follow. Means we do perform like this hazard, and means HARA, we perform like this hazard analysis and risk assessment. Once we do like this hazard analysis and risk assessment, we would try to, means first of all we develop like safety goals. Based on that safety goals, we try to perform this HARA. Once we identify, okay, these are the situation in which we might fail, we perform this failure mode effect analysis or fault tree analysis. And once we are like through that part, we would be assigning these ASIL levels, like and eventually if there are like some failures that could be avoided, then we would be doing like this parrot analysis, or like means there is a rice cooking method that's also available. So using that method, you would be like refining your requirements, and or maybe adding like more requirement for safety task. And that's how functional safety part is done. So functional safety is all about the failure that might occur. Okay, so functional safety is about that, and in order to avoid those failure, you would be adding some requirement through the pipeline that I just explained, like this HARA part, then this failure mode effect analysis, fault analysis, and then Pareto part, and then eventually this ASIL level assignment. And then you do iteration to add more requirements. So using this framework, what you ensure is that like you would have like minimum number of failures uh, in your actual system. So that's the functional safety. Next comes the sorting, that's the safety of intended functionality. And it's not something that occurs whenever there is a fault in the system. Okay, it's something all about, it's not about fault, rather it's about limitations of the sensors. Okay, I mean, for example, if I could give like one example, let's say there is a huge hoarding around the roads, I mean on the roadside. So in that situation, our sensors might have like wrong signals. Okay, or let's say there is a pothole and it's been let's say there is a manhole and then it's been covered with like that cover. So in that situation, we would our radar might have like wrong detections or like false detection, as if there is a vehicle standing next to us. And in that situation, if we detect like vehicle next to us, uh, we would be like activating our AEB feature, or we would be like decelerating our vehicle, and there are chances our vehicle would like stand, I mean just stop next to like manhole cover. And this is a limitation of like radar sensor. So inside Sorty, what we do, we try to understand all the limitations of our sensors or our system, and we try to ensure that something written its name, that's Sorty, safety of intended functionality. We try to ensure like basic functionality that's been like promised by that particular feature or particular sensor or particular module is being delivered. So basically we try to avoid like Sorty. So basically we try to do, so basically that's like sorted thing that we do. And the next thing, these are like two major things that we are using inside like functional safety or like inside autonomous driving to ensure that we are having, or we have added like enough number of requirement to ensure that our vehicle in its early stages have considered all the things that are needed to ensure or needed to make sure that it would operate very well in critical situations. So that's like FUSA and SOTIF, that's ISO 26262, and then this SOTIF, that's like 21884, I believe. So yeah, maybe 844, something like that, but that's like SOTIF. And then there is like NCAP and like these other bodies. Basically these are like regulatory bodies. NCAP is something is about like consumers performance test. So NCAP has like provided like certain number of tests that car is supposed to go through. Okay, so NCAP was like in earlier days it was about like safety. Now they have like, means it was about like performance, but nowadays they have extended it for like ADAS part, and they are like adding more and more number of tests to the NCAP. So whenever there is a new car, so that car is supposed to go through those number of tests, and based on its performance, and they could means just approve that particular vehicle. Okay, means whether that's like NCAP accredited or not. And similar NCAP is like for Europe, and similar standard is like also available inside like USA. That's like means NHTC is like providing some regulations for that. For like from this United Nations, they also provide like some regulations on that, like this work procedure 29. Or for EU, they have like their own means some version of like NCAP that's like developed for like this ADAS or autonomous driving. But these standards and regulations are there. That's something is like guiding this entire ADAS and autonomous driving development, and it's making sure that whenever this particular feature is being developed or this particular vehicle is being developed, it's safe to go on the road. And like there are certain safety metrics that we need to consider, and those metrics means whenever we build particular feature, whenever we try to validate this thing, we need to think about like various factors. That's like means first thing is about ODD. Do we have like full coverage? Means means I'm not talking about like means having like universal ODD, but also about like whenever we are talking about like particular geofence region, in that situation also, do we have full coverage for that particular ODD as well, or that particular operational design domain. So the ODD is something we need to look into. We also need to think about like various metrics. Let it be safety related metrics, let it be comfort related metrics or other metrics, or it could be about various challenges or some unseen cases or like edge cases. So we need to ensure like coverage over all of those things during those tests that are like recommended by like the standards and regulations. And once we are like able to perform this test, we would be able to like we would be able to assure that okay, that the feature that's been developed is like really is safe. Yeah, so that's the module 6. And now we would try to go to module 7, and inside module 7 I would briefly try to give little bit information about like latest trends. We are already beyond the time that we plan, but I would briefly try to conclude this part. Yeah, okay. Or I would try to finish this part. So module 7 is about like emerging trends that we have. So inside perception research trend, means as I mentioned, like earlier it was about like just classification thing, then it was about like object detection, then tracking part. But for all those tasks, I mean for machine learning, there is a branch called like supervised learning. And for supervised learning, we need to ensure that like there are proper levels to train that particular machine learning module. But creating those labels is like really difficult task. and it takes like a lot of efforts, and that's the reason nowadays research is going on to develop like these self-supervised algorithms, or like algorithms which are like unsupervised, like means there is like de novo architecture that's like entirely based on the self-supervised approach, so that you don't need to provide labels, but still you would be able to train your machine learning algorithms in a such a way that you would be able to get tasks done. So first of all, what it does is like basically you have input image, and then you would have like output image. You would feed it through encoder decoder architecture. You train your foundational model, then you slash your decoder part, and then you just use like your downstream module that you would want to get, like depth distribution in this situation or semantic segmentation, and you would still be able to get your task done. So that's like self-supervised algorithm that are being means that are being famous these days. That's like one trend that's there. Or training foundational models, so transformers for multimodal future. As I mentioned, like right now we do have like a lot of deep learning model that would cater particular sensor, but it would be really nice if you could have a deep learning model which could be used with like multiple sensors. Okay, so there is like BU fusion, there is a BU former. So this sort of algorithms could be transform based architecture could be used to deal with like data from multiple sensors, and would provide like robust representation of the environment. The next thing is like generative AI. So as I mentioned, like for autonomous driving and ADAS, the major challenge is about validating that particular feature. And to validate that thing, we would need to have like proper coverage. And to have coverage, we would need to create like test cases. And to create those test cases, we would need to create like varied number of scenarios. And best way to generate that scenario would not be coming from like that particular accident database, or like some recorded data like from Waymo database or like nuisance database. Rather, that should come from inherent capability of like foundation model to generate those scenarios. So that's something called like data augmentation, and these generative models would help us to generate those scenarios. And that's what we are doing in our present startup at Deontic.ai. We have generative AI based model. That's something would help us to generate data synthetically. The next thing is about like challenges. So as I mentioned, like these deep learning models would have like some issues, or like these particular sensors would have like certain issues, and to deal with that thing, we could we could like develop some custom models which would be like really robust against adverse weather, or like challenging lightning, or like some corner cases. So this is like latest research trends that are there inside perception part. Same goes for like prediction thing. Right now there is a huge research that's going on to develop world models, and in order to develop those world models, we would really need to understand the interaction between various uh, actors that are there in our environment. So we need to build like the social interaction models that would understand the interaction between various actors. Graph neural networks are like really good for that, but just having interaction information would not be enough. But we would also need to somehow interact, means integrate physics over there. So like current research is going on about world models. So this is also part of like this prediction pipeline. The next thing is about research train inside HD mapping. So I did mention like means we could use lidar sensor to generate HD maps of the environment, and right now research is going on where people are trying to generate these HD maps directly from the camera sensors, means camera images or like some lidar images. And means one example could be like GMAP algorithm that's there, where we would really be able to generate really precise representation of like a highway network with just the help of like camera images and lidar in like point clouds. So that's like research that's going on in HD mapping part. The next thing is about control. So for control, as I mentioned, the approach that I showed you, like we would have like multiple subsystems, and each of subsystem would have like some advantages. And when we talk about like this modular architecture is like really good when you would want to test it, whenever we would want to verify and validate it. But when we talk about like this modular architecture, that would lead to some compute overheads and like some unnecessary interaction, and that's something we could avoid if we use like some end-to-end architectures. So we could use like this reinforcement learning, means model-based reinforcement learning is something we could use for control part. Then we could also use like imitation learning. So that's like current research trends that is going on inside planning and control. And I also mentioned about like this end-to-end model. So yeah. So basically, people are trying to build like end-to-end foundational models. They are trying to build better world models so that they could predict the environment and then plan. And the final thing is about like scenario generation. So for scenario generation, huge research is going on inside diffusion part. We are also working on like diffusion models, and we are trying to generate simulation environment or like scenario which would be varied effectively just by varying prompt. And that's like current research trend that's inside scenario generation part. You could just go through like slides and you would understand more about that. And when it comes to like deployment and system level, means the challenges that are there when it comes to like deployment part. So we need to make sure that like the cyber security part is like taken care of. And when we try to put this deep learning module on like actual compute or like actual microcontrollers, it would need some time for inference. It would consume like huge power, and also it would need like huge compute. So we need to see how exactly we could integrate all those subsystems or ECUs, and what's the best way to communicate information with each other. So these are like some challenges, and since these are like challenges, there is also way, or like there is a like uh, research is being pursued in those directions to solve those challenges. But yeah, there are like new directions that are being explored with the help of like deep learning, with the help of like foundational models for perception, prediction, planning, and controls part, and also for like this architectural part, or like when it comes to electronics. And if I could like summarize, yeah, if I could summarize all the things that we have seen during this lecture. So first of all, we saw like the motivation. Why do we need to uh, build ADAS and autonomous driving? Because our final goal is to have vision zero. And what it means is like we would want to have like zero fatalities, and we would try to minimize the impact of like this particular accidents at societal level, at economic level, at ecological level, and also at political level. So in order to minimize those impacts, we would try to pursue this goal of like vision zero. And to pursue that goal of vision zero, we would need to ensure that we are building autonomous or autonomous driving feature which are like safe enough. And to build that thing, we could like classify that into like passive safety feature, active safety features, and like these automated features. And to build like features in much better way, we would need to understand what all actors that are at the play, like vehicle, environment, and driver, and how exactly their interaction is happening through that those four dimensions, like operational safety, perception safety, condition safety, and driving safety. And based on that, how can we build like better features, better safety features? And once we understand these things, in module 3 and module 4, we saw about like this entire pipeline. We start with perception, then we build prediction part, then sensor fusion, then prediction, then planning and control part. And in module 3 and module 4, we learn how exactly we could build actual pipeline which would deliver the autonomous driving capability or ADAS capability. And in module 5, we learn how can we build such complex system with the help of like system engineering, and how can we validate them with the help of like scenario based testing. And in module 6, we saw what all standards that are there and that are governing this testing, this feature development. And in module 7, we saw the path that are being currently explored to improve this autonomous driving domain in general, and to achieve better autonomous driving capability and put it on the road, and to like improve the trust, or like to increase the trust among general public. So that's like just summary for like all the things that we have seen inside lecture. And with this, I would uh, conclude this lecture, and now I'm open to the questions if you have any. Guys, do you have any questions? Yes, we would be discussing more about like HD maps in the future lectures. Yes, so we would be having lectures on localization and mapping. Over there, we would talk more about HD maps for sure. Yeah, guys, do you have like some more questions? About AutoSAR, we'll be doing something. I mean, regarding AutoSAR, I would give you like some resources, but we would not be covering AutoSAR in this like course. Means I could definitely give you like more information about like this AutoSAR framework, like traditional AutoSAR or like adaptive AutoSAR, but we would not be covering that thing in our current course. Maybe in future we would have like separate module for that. But yeah, right now we would not be covering AutoSAR in our present curriculum, unfortunately, because AutoSAR itself is like really huge thing and it would take like a lot of time to deliver it. Maybe I would try to include like small introductory section on that in our one of the lectures, but yeah, in general we would not be like we would not have like a dedicated section for that.
So in the follow-up, Mayur, thanks for a great presentation. Appreciate it. Would you like this one was for free, right? The next ones are for pay, right? I guess, or
Yes, yeah. So as I mentioned, so there would be like 17 more lectures, and I would try to take like gap between like two sessions so that I would put together like better content, um, and like add some tutorials as well. So next session would not be tomorrow, rather it would be rather means maybe on like Tuesday or Wednesday. But I would try to make sure that like I would deliver more about like machine learning, and I would try to put together better summary of like machine learning that's needed or like at foundational level. But yeah, to answer your question briefly, in order to attend like future lecture, you would need to enroll into our programs. I guess we already have like huge means we already have like most of guys from that paid program means who are already enrolled. But if you are not yet enrolled with us, then you definitely need to enroll with us.
okay, got it. Thank you.
Yeah. Okay, thank you, Amit, for question. Yeah, Shivam, yeah, tell me what's your question.
Mayur, thank you for the lecture. It was very good. I wanted to know if there is any lecture plan so that we can schedule our days according to your lectures. I
Okay,
mean,
so next lecture would be about machine learning,
okay,
and machine learning lecture is something I'm planning to conduct on Wednesday.
okay,
And in Wednesday, I mean, on Wednesday also it would be for like 2 or maybe 2.5 hours. That's
okay,
something I would be taking to deliver that content. But in
okay,
machine learning, I would make sure that I cover everything that's needed. Uh,
okay.
yes, it would be on Wednesday.
So you
And
will be
there is like,
discussing about the next lecture
yeah.
in like the previous one, right? Like, or are you going to give the plan for the whole lecture sessions?
No. I would just be declaring like one lecture at a time. Means whenever we are done with like this one lecture, I would be telling like when exactly we would be having like next lecture. So for like machine learning, it would be on Wednesday. I would be
Okay.
taking about like 2 or 3 days because I mentioned it already on a group that I would want to put out content which
Uh-huh.
is like really comprehensive, and I would
Okay.
just not follow timeline. Okay, means I would try to have content which is helpful.
Okay, that makes sense. And also, like you said, our next lecture will be on Wednesday. So, is there any prerequisite that we should know before attending that lecture so that we understand it in much better manner?
It would be really nice if you have like some primer in probability or like in general about like statistics, so that it
Okay.
would be easier for you guys to like understand that thing in much better
Okay,
way.
makes sense. Okay,
Yeah, yeah.
thank
But yeah, I mean, right now, since I would just want to show you like some more things. I mean,
you.
regarding this, which is like follow for this particular session, and it's about what else thing that you guys need to do. Okay. So you all of you have like access to our Google Classroom, right? Can you just like put thumbs up or something so that I would understand?
Yes. We have access to the Google Class. Like at least I
Yeah.
have.
So over there is a section called classwork, and over there I have added like some topics. Okay. So generally just about like general information, how exactly you could install MATLAB and IPG car maker and lecture and project plan. But then this fundamentals of programming and data structure is something I added over there. So I was expecting you guys would like go through those lectures and those tutorials that are there. And then this is like our current lecture, that's fundamentals of autonomous vehicles. So inside lecture 1, you would be seeing like all the content that I just shared with you. That's like means PDF or PPT, like PDF for that current lecture PPT is added over here under intro to AV. If you need like brief notes, then those notes are added over here. uh, and if you need like summary of like this entire thing, like very brief summary of like 5 minute summary, then that's added over here. And apart from that, if you need like better mind map to remember this thing, then it's also added over here. Okay, and I did share like PDF version of this thing on a group. I would also add it over here, but this is a material that's available if you want to like go through this thing again. And if you are sure like this much information, or like if it's enough for you to just like attend this one lecture and you have like understood it like entirely, then what you could do is like you could go to this quiz section, and then you have like around means 30 questions over here, which are like multiple choice questions. But that's something would help you understand means how well you are with all the content that we covered in this lecture. So you would have like quiz for each of those lectures. Sometime you would have tutorials, but you would need to finish this quiz before our next lecture. Yeah, this is for like everyone. So guys, just make sure once you finish like entire content, just go through like that quiz, just finish it. And once it's done, then yeah, it would be easier for me to yeah, just keep track of everything, so that I could give like certificate in the end, once I'm sure like you guys have like understood this thing well. Yeah. And
Sure.
regarding like recordings, when they would be available, I guess it would be available maybe like tomorrow morning. It would be available. Yeah, lectures would be available tomorrow morning because it's in a cloud right now. So I need to download it. I just need to yeah, I just need to process it little bit, and then I would put it on a Google Classroom. Yeah, so it would be available tomorrow morning. I just have like one simple request, because I'm not putting like really strict means restriction to you guys, that like means the content that I'm uploading to Google Classroom. I really request, just keep it to yourself. Just don't share it with others. Already, I mean, for me, like means whenever like this in-person session is done, later on I would be like giving it away like for as an online course. But right now I would really request, just don't share this content with others. They would also have capability to like get this content later on when they enroll. Yeah, it's just like one request, just don't share it with others. Yeah. And to show that like you have understood or learned something from this program, you could like very well show that thing with the project that we would be doing during this program. Like we would be doing project on ACCAB. So that's something you could put out on your Git, and you could show it to the like employers, or like if you are like looking for a job, or you would be doing like your own project on LK. So that's something would also be, can be, means would be put out on like GitHub, and that's something would give like good credibility. But yeah, means in general you don't need to put out like other content outside. And mind map and other material, something you could use for yourself to understand concepts better. Yeah, I should ask question.
So you mentioned about the project ACC.
Yeah.
I have this question like which control are we going to use for the particular control algorithm?
For ACC.
Yeah.
For ACC, it's about like longitudinal control. So as I mentioned, first of all, we would be using like state flow to decide between this headway control and cruise control mode. And then we would be
Okay.
using like PID controller. For ACC, we would definitely be using a PID controller. That's like simplest thing that we could use. But if you would want to use
Okay.
MPC, if you would want to use
Uh-huh.
MPC, then I would definitely like to, means if you need any help to implement MPC, I would definitely help you. Okay, I would really not have any problem regarding
Yeah.
that.
Okay. That's what I was asking because I tried using MPC for the ACC algorithm, and
Mhm.
so I just wanted to relate few things. Yeah. That's all.
Yeah. So if you need like any help implementing MPC for ACC part, I would definitely help. But the
Yeah.
thing is that like means MPC thing itself is like quite huge thing. Uh,
Yeah.
yeah. So I just don't want to go into details about like all those optimization
Okay.
algorithms
No
and other
problem.
stuff. So that's the reason I wanted to go ahead with like simple things, so that our focus would be more about like ADAS, and not about like control part and other stuff. But if you need like some information or like some more content on MPC part, I would definitely be up for that. No worries.
Okay. And one more question, Mayur. I just wanted to put this in brief. Like, is this course about the development, or is it about the testing part? Which part are we going to focus more? Like, I mean, there are multiple ways to develop things. There are multiple ways to test the things. So, is it
I would say like means we would be doing like development, and we would be giving like more attention to the development,
okay?
and we would I would show you like all the steps that you would need to follow to perform the testing, but
Okay.
I don't think like we would be able to perform like entire testing for that particular feature. And the reason for
Okay.
that is like let's say you have like ACC or AAB feature. In order
Mhm.
to verify and validate that feature, you would need like around 4,000 or 5,000 scenarios at minimum. Okay, at
Okay.
lowest you would need like 4,000, 5,000 scenarios, and we don't have time to generate this many
I understand.
scenarios.
Yeah. Okay.
And I mean, I do have a platform. I would have like access to Deontic, and I
Okay.
did like spoke to CEO of Deontic, and he did say okay he would allow us to use Deontic platform to generate scenarios, but he said okay
Mhm.
we could generate like 10 scenarios per person, and
Okay.
that would really not be useful. But that would something just give you like idea how exactly you could use generative AI to generate those scenarios.
Okay.
But yeah, so we would be doing development entirely. We would follow all the steps, and for verification and validation, we would follow steps that are needed to verify and validate that feature. But we would not have full coverage over our ODD.
Okay. Thank you.
Yeah, and like other two questions that's coming from like Ashwin. Oh yeah, so it's tomorrow morning for recording, and for Junaid. I would try to have like two lectures per week, 3 days to like means yeah. As I mentioned, like I'm on vacation, but I would still try to put together content, which would be like helpful to everyone. So I would try to do like 2 to 3 lecture per week. Yeah, yeah. That's the plan. Yeah.
Yeah,
Yeah.
hello.
Yeah.
Hello, Moi. This is Vishwa. So, Vishwanath. Uh, yeah, it's a nice lecture, Mayu. Thanks.
Yeah. Welcome.
Regarding like my worry is like about timings because I'm staying in Vietnam, so currently it's 1:30. So, is there anything like one half an hour like start early something?
Mhm. Okay, Vishwa, I would do like one thing over here. Okay,
Okay.
I would try to make sure that the content that we plan should be for 90 minutes, and we would not go beyond that. That's one thing
Yeah.
that I
Yeah.
could do. Second
Okay.
thing that I can do for you is like I would try to upload recordings as early as possible.
Mm-hmm.
And third thing that I could do is like I would be available for like your queries after these means these sessions as well. Means whenever
Okay.
you go through recording, if you have like any queries, you could just text me on your my personal number, and
Yeah.
we
Yeah,
would
okay.
use
Okay.
them.
That's great. That's great.
Yeah, and it's
Yeah,
for like
because
everyone.
sometime like
Okay.
yeah,
Yeah. If,
if I'm not able to concentrate on the lectures, like I can go through the recordings. I can come back to you.
yeah, yeah, definitely. And this is for like everyone. If you guys are not able to attend it, and later on if you need to go through recording, and if you're not able to understand particular thing, you could just like come to me. You could just text me, and I would answer you. Yeah, that's something we could do.
Yeah.
But right now, I'm really sorry if I were having like multiple people from like one time zone. I would have like created
No,
like batches for
that's
that.
great. That's
But
fine because now
yeah, yeah. Right now
recordings
we
are
just have
available.
like 15 or so people for this course, and they're like in multiple time zones. So I really cannot have like separate batch for each of them. But yeah,
it's
I'm
fine.
sorry for the inconvenience that you are having.
No, that's what like you resolve. No, so like I can go through the recording. I can contact you
Yeah,
directly.
yeah, perfect.
Yeah, that's fine. Okay.
Yeah, thank you. Yeah. Yeah, guys, if you have more questions, then ask me now. But just keep one thing in mind: you can go through content that's available in Google Classroom. Second thing, you need to finish quiz before like next lecture. And if you have any question, you could just put it in our common WhatsApp group, and then I would answer them over there. Okay. And if you like want to answer question that your colleague is not getting or like having trouble with, you could just answer it. Okay, and that's also welcome. Yeah, so guys, thanks a lot for your time, and sorry for the inconvenience that we are running like 30 minutes late. But yeah, I would try to be in
Uh,
time from next time, and with this I could like conclude this session if you don't have any question. Vishwa, do you have any question?
my Yeah, just like one thing, like yeah, today like content wise little more I feel. uh, Sometimes like I feel like maybe some interactive session, like maybe in the next session
Mm-hmm.
in between, like maybe you can ask some questions, like you can like just kind of like what can say suggestion, like
Yeah, yeah, definitely. I
yeah,
really wanted to be like as interactive as possible, but yeah,
yeah.